Jonathon Wilson, who is a research associate for the Optical and Thermofluids Research Group at the Loughborough University. Jonathon is currently working with enterprise funding to develop ACCT technology, which was invented and developed as a direct result of his PhD research conducted under a Loughborough University scholarship. So the floor is yours, Jonathon.
Brilliant. Thank you very much. And thank you for all of those that stayed around. I know the football's starting soon, and I know everyone wants to go home. I certainly need to get off on time because we're going to race for the ferry, and I'm reliably informed that we're not going to make it. What I want to talk about today is a new NOx reduction technology system. We've been sort of muttering about it for a year or two, but we can share a little bit more information today. It's very similar to the results shown by the European Commission. Our goals are the same as the retrofit prize winner. The only difference is our goal was to use AdBlue the whole way through so that the user doesn't see any form of difference in a standard AdBlue-based SCR system. As a bit of background, I'm sure few of you have heard of Loughborough University, but we are an optical diagnostics group for thermofluids, and there's lots of words in that. Essentially what it means is that we are a thermofluids group looking at thermofluids problems, but we're using a set of laser-based and optical diagnostic tools, such as things like phase Doppler interferometry for particle size analysis, such as high-speed imaging to watch what's going on inside flows, and things like PIV to actually watch exactly what's happening within a flow, within a system. Specifically, we have a facility that is dedicated to SCR after-treatment development. It's consisting of 2 rigs. Each one is capable of generating an airflow that simulates a diesel exhaust flow, up to 600 degrees, up to sort of the 7.5 litre engine, 900 kilograms an hour airflow rate, with the ability to tee the 2 rigs together to produce a 15 litre equivalent engine. We're using airflow. We have gas burners as well. We don't use them very often. Mostly what we use is electrically heated air because it keeps the flow nice and clean for the optical techniques we use to analyse exactly what's going on within that exhaust system. So I think the majority of people here are very, very familiar with the problems involved with injecting urea into an exhaust system. Simply put, what we're trying to do is turn urea into ammonia. That is a 2-step process. First thermolysis and then hydrolysis. Now thermolysis is fairly easy. You get it hot and it starts to turn into other stuff. Hydrolysis is a bit more complicated. We need to provide the right environment for that to happen, and that can lead to the formation of all the secondary deposits. So you get it wrong, you form isocyanic acid, and if you don't manage to hydrolyse that isocyanic acid, it is, I like to call it a gateway drug. It's involved in the formation of all of these secondary products. And the further down the line you get with the secondary products, the harder they are for you to remove from your exhaust. So if you've got cyanuric acid, you can probably regenerate that. When you get down the line towards the melamines, that's very, very hard to get out of your exhaust system. So just to show some of the optical techniques, this is what happens inside your exhaust. This is a 30-minute test, not at a problem condition at all, but it is with a simplified mixer that we've used for back-to-back, non-commercially relevant tests. Within 30 minutes, you notice that this spray has 3 very distinct mass flux peaks, so it's very directed onto the different veins of the mixer. And at the centre of each one of these peaks, we're starting to form essentially wet urea, and the urea involves itself in the secondary products as it forms isocyanic acid, and you start to form deposits which are quite difficult to remove. And you see the yellowing on these deposits is indicative of somewhere around some melamine formation, some things that are not simple biuret, triuret, CYA. The system we've been working on, this is a nice sort of simplified animation. It doesn't look like this anymore. In short, what we're trying to do is convert AdBlue into a second solution. That solution is ammonium carbamate. Ammonium carbamate looks physically very, very similar when it's in a liquid to AdBlue. Injects almost the same, but is much, much more reactive than AdBlue is when you inject into the exhaust. It decomposes only by thermolysis, and it decomposes from 60 degrees. In more detail, what we're doing is we're feeding AdBlue from the DEF tank, standard DEF tank, standard AdBlue tank, present on any Euro 6, Euro 5 car. we're feeding that into a reactor. Now this reactor, what we've done is we've kept the conditions inside there at an optimal point for thermolysis. So what we're trying to do is increase the pressure slightly to increase the availability of water. We repress the boiling point of water very slightly, so there's more of the liquid side of things. It's got lots of surfaces available for that thermolysis reaction to occur, because isocyanuric acid only thermolyzes on a surface and in the presence of water. And it's got a much, much longer residence time. So in there, you've got, in thermal contact with the exhaust, you've got the heat going in from the exhaust, downstream of the catalysts. We're slowly decomposing. It takes about 5 minutes to fully decompose one ABLU molecule as it passes through the reactor. The output of the reactor is then ammonia, carbon dioxide, and water. The great thing is, when you start to cool that down, the ammonia reacts with the carbon dioxide. And when the ammonia reacts with the carbon dioxide, as we reject heat, it starts to form ammonium carbamate. And ammonium carbamate immediately dissolves into the steam as the steam condenses out, and you get an ammonium carbamate solution. In that solution, the elements, it's basically an ionic solution. It shifts very slightly in its composition. It's not pure ammonium carbamate when it's in there, but it acts exactly like an ammonium carbamate solution you would have mixed up with a lump of ammonium carbamate and some water in the lab. We can then dose this system back in. We can dose the ACCT fluid back into the exhaust at any point we like. We've got two strategies for doing that. The first one is we look at a strategy where we do a split dose. So at the conditions where we're confident that ABLU works perfectly, we don't want to mess with it at the nice high exhaust temperatures. For the larger engines, we might as well dose ABLU, save the bother of going through the system of converting it. For the smaller engines, it might be preferable to solely dose ACCT fluid at all points during the cycle to try and simplify the injection side of the system. We're aiming to install this downstream of any catalytic components because we'd rather the heat gets into the catalyst, activates the catalyst as quick as possible. Because if we've got ammonia radiated from 60 degrees, that's certainly a lot lower than you have catalyst activity from. It works at much, much lower temperatures than the typical injection of ABLU. Because when you inject ABLU into the exhaust, you've got in the order of a couple of milliseconds to turn that ABLU from urea into ammonia. In the reactor with 5 minutes, we can do this with a much lower grade of heat. Let's say the reaction starts from 120 degrees and the rate ramps up equal to temperature. So by storing this solution ready for injection at any point, so you can start injecting from as soon as your catalyst is active, we can operate with a much, much lower heat on the reactor and try not to waste heat from our exhaust that we desperately need at this point. At the moment, we've been through a couple of cycles of prototypes. We started off with a nice pretty blue cycle, which was to go, look at this, doesn't it look nice? Worked very well, but the rate was quite slow. It wasn't in very good thermal contact with the exhaust. We went quite rapidly on to a much more realistic prototype, and it's put down there in the bottom left. That was as it was being welded up. The flanges are for our universal adapter system to fit into our rig. All it is an annular reactor that sits around the exhaust. There's zero restriction in the exhaust line, and it provides the space, the conditions, and the requirements for that thermolysis and hydrolysis of ABLU. We've now moved on a little bit further. We drove here today in our research vehicle, which is now equipped with ACCT injection. I say now, it wasn't on Friday. We were there quite late, finishing it. Otherwise, we wouldn't have been here today. Made the ferry with minutes to spare. We're going to do the same on the way back, I imagine, but we're just starting to collect data from that, and then we'll start releasing it as soon as we've processed it properly. But we're aiming for pretty much 100% NOx conversion in almost all conditions. It's entirely reliant now on the catalyst, so as long as we can get heat into the catalyst, we can do NOx conversion. The difference is quite apparent. So this is a nice cold surface, 160-degree surface. This is a droplet of ABLU and a droplet of ammonium carbamate solution. That's back exactly the same. You can see that the droplet disappears rather quickly when we drop it onto a hot surface. Whereas ABLU, that video will run for about 3.5 minutes now. And after 3.5 minutes, you're left with a nice white stain deposit, as you'd expect from a not properly decomposed ABLU droplet. If we zoom in, do this in a little bit more detail. These are high-speed videos. These are backlit sonography type work so that we can see exactly how the decomposition is done. It's done at about 4,000 frames a second. So what we see is when the ACCT fluid hits the surface, we've got a bit of a thinking change as to how ABLU works, as to how the ACCT fluid works. Because we model ABLU as the water boils, then we melt the urea, then we start to decompose the urea as a simplified model for its decomposition. With ACCT, because the volatility of ammonium carbonate is much higher, the first thing that happens is the ammonia off-gases. So what you can see there is the droplet is foaming up. It's basically an effervescent process. Ammonia bubbles are being spontaneously created inside that droplet as it warms up. None of the water is boiled off yet. It's just releasing the ammonia first. If we give it a few seconds, and I think this happens at about 100 minus 100 milliseconds, so we're getting very close, we're going to see a change in how the droplet boils. So it'll swap from that foaming action to a water boiling action. So you can see the point 400 milliseconds in, we've now got rid of all the ammonia, and we're left with a little bit of water, and the water boils off exactly as expected. In the case of AdBlue, what we are left with is nice molten urea sat on the surface. It's going to sit there for a very long time. It's beyond the memory capacity of our high-speed cameras to record the whole event. It takes quite a long time. We can do this again on a much, much colder surface. It's 118 degrees. And remember, this is the surface temperature, not the surrounding air temperature. So the surrounding air temperature is even cooler. So the system, it's a worse case scenario, basically. So as we drop it on there, within 5 milliseconds, we're generating ammonia from the ACCT video. Now, the AdBlue one, I'm afraid that is an incredibly boring video, so I won't make you sit here and watch it. It does very, very little for the entire process, really. If we watch it for the full half a second, you might see one little bubble as the water starts to warm up. Looking at this back in the lab using TGA. TGA is a method for basically assessing the decomposition of droplets. It essentially weighs the droplet as it heats it up and things. What's important to note about TGA is that it's measuring the cell temperature, not the actual sample temperature. So the sample temperature lags behind. So the temperature gradient at the bottom, that's basically arbitrary. It's defined essentially by the rate per minute. But it does give us a good idea of the process it's going through for the decomposition. With AdBlue, we can see that there are several steps. We can see that we've boiled the water off to start with, then we've got the molten urea step as the molten urea starts to off-gas, then we're left with some deposits which are much more complex, and then we're left with a really stable, complex deposits at the end which are incredibly difficult to get rid of. And actually that graph never goes to true zero. It gets fairly close, but it leaves a few micrograms of stuff left in the bottom of the crucible. The difference with ammonium carbonate solution is because it's a one-step process, because it boils very, very rapidly. It's that nice smooth curve, that nice predictable release of ammonia that can be quite easily modelled and quite easily simulated in the whole exhaust system. So you do it basically with evaporation and using a modified specific heat capacity. So it's all very well to look at the droplets. I quite like looking at droplets, but it's much better to show it in an exhaust system. This is one of our optical setups. So this is running on the airflow rig described earlier. It's an optical section, so it's the injector, so we can watch the injection, we can watch the spray as it comes out of the injector. It then hits a impaction mixer. This is using a sort of 100 micron droplet size with 3-hole injector. Hits an impaction mixer, and then 800 mil downstream, we've got chemical gas sampling that we've done by duct scanning. Because this is a generic mixer and we've obviously simplified the bend input, the angle, the ammonia uniformity is fairly shocking. So we've done a full scan across the duct to find out the average ammonia concentration of the airflow. What we show is if we start by looking at the veins, in almost every case in this simplified setup, we form deposits with AdBlue. It's very, very difficult to get to do that with the ACCT solution. What we do get is, because of this very concentrated jet from the injector, we get a bit of localized cooling of one of the fins. I'm not sure why it's only one fin, but I imagine the injector's missing the other two a little bit. That cooling means that you get boiling on the back of that fin. This is the component that's moved around, and as it's getting enough heat to fully decompose, the energy is about the same requirement as you get for AdBlue. It just boils off the ammonia first, leaves a little bit of water film, and then the water film boils off. With AdBlue, you get the edge effects, where the edge effects start to form deposits. You get your liquid pool, and then around the edge, the small amount of deposit formation. I think everyone in the industry has seen this to some degree. The response is quite interesting. What we've shown is that we can actually get a good amount of ammonia fully released into the exhaust down at even 100 degrees exhaust temperature. Now, there's a small gap between 100 degrees C and 150 degrees C. Now, that goes back to the wetting on the back of the face. So it's storing a very, very small amount of ammonia at these incredibly low exhaust temperatures. As we go up in temperature, there's plenty of energy to get rid of that, and we get almost the full release from 150 degrees. Now, this is very, very different to what we see by AdBlue. I think AdBlue in itself, if you do exactly the same test, back to back, or even for longer tests, this is a longer version, what you find is that the release is much, much lower. The release is typically about 25% of free ammonia in the exhaust stream at 800 ml downstream in the mixer. Now that's without adding things like hydrolysis catalysts. You can start to improve the situation with advanced mixers, advanced hydrolysis, advanced impaction, but it's still not 100% release. In this case, there's almost zero thermolysis going on in that exhaust flow. It's entirely reliant on the front face of the SCR catalyst to finish the thermolysis. And we're also getting small droplets of, there's a few papers out there that theorise that this is microscopic droplets of urea, molten urea, travelling through the exhaust. There's some proof out there for that with liquid quench chromatography showing that at these sort of points there is urea present in it. There's also a possibility that some of this is being deposited on the wall, is being involved in the secondary reactions, that it will be released when we go through a regen cycle maybe, which gives you a bit of unpredictability in your dosing. But what is quite repeatable is that the actual percentage of ammonia in the exhaust is nowhere near the 100%. This should be around 450 ppm complete, for a completely decomposed flow if you work out the mass airflow plus the injection rate. In the real world emissions, I'm blown through that quite quickly, but that's okay. We might make our ferry. We've done some testing on a retrofit. This was a retrofit up in Penrith. It was one that we had the ability to play with for only a short amount of time, so this is a partial system fit. So this is basically the full injection side of ACCT, but without the generation on there. The generation's been done in the lab on an equivalent system. When we inject this into the exhaust, this is worst case scenario. This is -3, there was snow, sleet. This is in the north of England before Christmas when we had the horrible weather conditions. The motorways were closed on the way up there. We drove around Penrith at about 0 to 20 miles an hour, stop-start traffic, and we found we got nearly 100% conversion. The total figure is just over 98, and the reason for that is we were using a standard AdBlue controlled dosing system just with the temperature limitations for dosing removed. That doesn't quite keep up enough with the NOx production. You need a slightly sharper injection rate. So with a slightly higher frequency injector, we should be able to get rid of even those remaining peaks on this graph. Okay, that was a fairly quick overview, but I'm happy to take any questions.
Thank you very much.